We'll now begin Chapter 26, concerned with direct electric currents. Our first section here will be on a module for Kirchhoff's laws. Kirchhoff's laws are pretty straightforward and simple, and they're really common sense. The first of Kirchhoff's laws are that the sum of all currents entering a junction must equal to the sum of all leaving the junction, or node. Well, if we imagine that we have an electrical circuit and we have current coming in, and here's a node or a point, Kirchhoff's first law says that the current I that comes in must equal to I, the current that goes out. Now, what would happen if this were not true? If this were not true, it would imply that the charge that's coming in is not the same as the charge going out. And since charge is conserved, then this would be a problem because charge would accumulate at the node. So basically, this is a statement of the conservation of charge. And we would get the same problem if we had 3 coming in and 2 going out, so that this was, say, I1, this was I2, this was I3, this was I4, and this was I5. Then, taking the positive or negative, let's take positive as coming in, then we can simply say that I1 plus I2 plus I3 plus I4 plus I5 is equal to 0. Where in this particular case, we'll notice that I1 and I3 and I4, this one, and this one are positive. And I2 and I5 are both negative because they're both going out. And so this is an equivalent way to write Kirchhoff's first law, that the algebraic sum of all currents entering a junction is equal to 0, meaning if they're coming out, they would have the opposite sign. So this is the first of Kirchhoff's laws. The second of Kirchhoff's laws is the sum of the voltages across each element in any closed loop must be 0. That means that if we have, say, a battery here, we go around here and we may have a resistor, we may have a capacitor, we may have an inductor, we may have another resistor, whatever. And we may even have a connection that goes from this point over to this point. We can choose any loop that we want to. We can choose the whole loop around this whole path, or we could choose the loop around here, or we could choose the loop around here. And whichever way we consider those loops, it's always true that the sum of the voltages across each element in that loop must be 0. So let's take the whole loop first, and let's look at this as the voltage across resistor 1, voltage across the capacitor, voltage across resistor 2, that's the inductor, and voltage across the resistor 2. This would be the voltage in the battery. So we would see here that the voltage plus the voltage from the battery, I'll put battery there, plus the voltage across the resistor 1, plus the voltage across the capacitor, plus the voltage across the inductor, plus the voltage across resistor 2, the sum of those must be 0. Now the sum of those can only be 0 since we have a positive voltage across the battery if some of these other voltages are negative, and in fact they are negative. They're negative because they have a voltage drop that's in the opposite direction of the battery. And so the battery puts a voltage in one direction. This might be, say, a 12-volt battery, and this might be a -2, a -3, a -3, a -2, whatever, but these other voltages have to add up so that they exactly cancel the voltage of the battery. The battery is always going to give you a positive voltage. Other things resist the battery, so they will give you a negative voltage. Another way to say that is you could write the voltage of the battery is equal to the sum of these others where they are all positive. But we've written them as negative here because they're opposing the battery. This is Kirchhoff's second law. There are two instruments that I won't go into great detail on. They're basically built upon the concept of a galvanometer. A galvanometer would have like a small coil with a hand that goes through it and another coil that came around the side of it. And when a current flows through this coil, it causes this coil to have a magnetic attraction to this other coil, which has a constant voltage through it. And the hand will swing over here. By adjusting these coils on this galvanometer in different ways, we can make out of this galvanometer a meter to measure voltage or a meter to measure amperage. So the galvanometer is the core instrument that's used to make both a voltmeter and an ammeter. Now let me mention something about household wiring. All the wiring normally in a house is 110 volts, except for when appliances really need to pull a lot of current, and then we use 220 volts. We use 220 for an oven, air conditioning, and some other very large appliances. And these would be your large heating elements or large air conditioning elements, your furnace, or what you might call your heat pump. All of these are going to be 220. They will have a large breaker, and actually it's a pair of breakers that are usually govern these that are right together. So this pair of breakers here would flip positive and negative to turn them on and off, or say an on and off position. But generally speaking, these are lined up. But what you have in practice is you have three wires that are coming into your house. This is a ground wire, and I could write that, can't really read that, G-R-O-U-N-D. The ground wire is connected to the earth. And this is a plus 110 volts, and this is a minus 110 volts. So between these two outer ones, there's a 220 volts that we can use by going from the outer one here to this one. Or if we just want 110, we pair the breakers in the house, or the different circuits, as I should say, either from this side or from this side about equally. So one or two of the bedrooms might be a breaker here, then the next bedroom or two might be another breaker on the switch, and then you might put a third bedroom on another breaker and a living room on still another breaker. And so these are spread out throughout the house. And this is the way the circuits are designed in the house, so that we don't have any voltages higher than 220 inside a normal home. That is a happy compromise, as I mentioned the other day, between having a real high voltage, which means that we don't need much wire in order to carry the current for that given power, but the voltage becomes risky in terms of arcing and electrocution. On the other hand, if we get lower voltages, the wires have to be so large, we run the risk somewhat of having a fire. So this takes us through our concepts of Kirchhoff's laws and finishes modules 26.1.